Hello everyone, I'm Peiqi, the co-author of this workshop paper, NeSyPack, a Neuro-Symbolic framework for bimanual logistic packing. So we have used our framework to win the first prize in the ICRA WBCD competition, and the main focus of this competition is bimanual manipulation. And we have deployed our framework on the G1 robot during preparation stage and the Galaxia A1X robot arm during the competition stage. And our framework can easily adapt to different objects and different robots. So the main focus of this WBCD competition is to pick and place diverse kinds of objects into a packing box and then finally seal it. And these objects may have diverse requirements, such as something need to be separated using two arms and something need to be carefully packed or need precise manipulation. And the scoring metric is based on the mode you use and the number of required items you finally packed in and the task completion time. So the one big challenge of this competition is how to efficiently adapt to different objects and different robots. Some of the work would choose to use to train a large VLA model with a large-scale data set, but our focus is to how to efficiently adapt to diverse object manipulation with our large-scale retraining. So to solve this challenge, we propose a Neuro-Symbolic framework to structure robot skills in a modularized and interpretable way. And it can facilitate efficient planning and can be easily extended. So the core component of this pipeline is the robot skill graph. And this skill graph stores 6 components: skills, objects, embodiment, tools, executors, and sensors, and together with their relationships. So the core components of it is the robot skills. We define a skill as a parameterized goal-directed capability that can transfer the war state or change the robot's internal knowledge about the war. And the role of the skills here is to represent a high-level semantic robot operations. And we divide the skills into 3 aspects: perception skill, manipulation skill, and motion skill. So a skill is just a verb, and it just has a semantic meaning. To physically ground it, we need the skill to interact with the real world. So we also define the objects as the items to be packed in the competition, and each described by their properties. And to further ground it, we need to define some hardware that can support the grounding of the skills. And we store 2 kinds of them. One is embodiments that define supported robot configurations, and one is tools that specify the available end effector. And to finally ground it, we have to have some grounding code, and that is the executor that can link each skill object set to an executable function, and it can incorporate the embodiment tools and feedback sensors. So here we can construct our robot skill graph, and based on this, we can do some high-level planning. So whenever a task comes in, our hierarchical task reasoning module can serve as a planning module, and it can decompose the task into several subtasks and decompose the subtasks into further atomic skills and then query the robot skill graph. And the robot skill graph will choose the most feasible embodiment tools and sensors based on the skill object set, and then choose the final grounding executors, and then send the control signals to the robot platforms, either in simulation or real robots, and then collect the feedbacks and send it back to the task planning module. And the planning module can choose what's the next step based on the feedback. So you can use your own planner or even LLM, but here we use a state machine to do that. So our pipeline can achieve a good performance during both the preparation stage on G1 robot and also during the competition on the Galaxia A1X arms. And we have tried the pipeline onto diverse objects, and it can achieve a success rate at around 19%. So to sum up, our pipeline can achieve a very high generalizability with both task and hardware generalization, and also a very high data efficiency with just a few shots learning for perception and 1-shot adaptation for manipulation. And also, it can achieve a very high reliability with over 90% text success rate, and it can be easily extended with a seamless integration of new perception and manipulation skills. So for our next step, we want to do some autonomous population of this robot scale graph, and also we want to do some autonomous robot scale learning, and also we want to enable the whole body control. So that's all of my presentation. Thank you.
All right. Now we will break for coffee, go look at post